The reflection of waves is when the wave encounters a boundary and bounces off of it. Waves are only reflected at boundaries. So a boundary is just a medium density change. When a wave hits a boundary, if the density of the new medium is greater than the density of the original medium, when the wave reflects, it will flip. When you do the wave properties lab, you will see this, or if you've already done the wave properties lab, you will have seen this. If the new medium density is less than the original medium density, when the wave hits the boundary, it will reflect and it will also be transmitted, and the reflecting wave will be in the same orientation as the initial wave. If the new medium is less dense, then again, the reflecting wave orientation will not change, but a larger percentage of the wave will be transmitted rather than reflected. In the first instance, when the new medium density was greater, the largest percentage of the wave will be reflected and only a small portion will be transmitted. The next thing we're going to take a look at is what happens when two waves meet. And it's talked about or described as the principle of superposition. What happens to the amplitudes of two waves when they meet? When two waves meet, we talk about that as interfering. There are two different types of interference that we can talk about. The first type of interference is described as constructive interference. For constructive interference, we have, in this case, we're looking just at pulses. So we have a positive pulse heading to the right. We have a positive pulse from another wave heading to the left. What happens when those two pulses meet? At the instant where the pulses are superimposed or one on top of each other, or they are then both in the same space along the medium, their amplitudes will add. So what we will see is an addition of their amplitudes. Since both are positive, the pulse amplitude at interference will be the sum of the two pulses. For destructive interference, this time we have a pulse headed to the right that has a positive amplitude. We have a pulse headed to the left that has a negative amplitude. So when they meet, when they interfere, again, we're going to have addition of amplitudes, but one is a positive value, one is a negative value. So in this case, where the positive amplitude is the same absolute value as the negative amplitude, we get something that looks like this. If their amplitudes are not the numerical same, then you will have either a slight positive or a slight negative amplitude at the point of destructive interference because they don't equal each other out. Destructive interference means that the net amplitude is smaller than either of the original amplitudes. Constructive interference means that the net amplitude at interference is greater than either of the two original amplitudes. Our next topic here is taking a look at traveling waves versus standing waves and how are they different. For traveling waves, we can tell if a wave is traveling because we can see its motion through the medium. And normally what we see are the crests and the troughs as they move through the medium. We can tell which direction it's moving because it's going to be one direction, moving away from the source. A standing wave is when we have a wave or a couple of waves that have the same frequency, same wavelength, the same amplitude, and they are either one wave is traveling and reflects upon itself, or we have multiple waves traveling but in opposite directions. What we observe is motion. So we can see an oscillation from crest to trough of the wave, but we can't tell a directional motion. So motion is visible, but directionality is not. So if we start this wave, it starts out as a transverse traveling wave. We know it's a traveling wave because we see the motion of the medium perpendicular to the direction of the wave motion. Wave is moving left to right. Medium is moving up and down. When this wave hits the barrier, it will reflect. In this case, the barrier is a more dense material, so the wave has flipped its orientation. The blue is the reflecting wave. The red is the incident or initial wave. The black dots show us the constructive and destructive interference when the incident and reflecting waves meet. Because we can identify incident and reflecting waves as incident being red, reflecting being blue, we can tell directionality. But when we see something like this in nature, whether you're shaking a rope or vibrating a slinky or plucking a guitar string, you don't see the incident and the reflected waves. All you see is this black dotted line that's shown here, which is the constructive and destructive interference of these two waves. And all you see is just the oscillation of the amplitude larger and smaller, and then going from crest to trough. And that's what we call a standing wave. We can tell it's a wave, but we don't see any directional motion. So in our diagram here, the blue is the incident wave, and the green is the reflecting wave. The other two parts of a standing wave are the nodes and the antinodes. The nodes are the points the wave crosses the equilibrium point. So this is a node, this is a node, this is a node. The antinodes are the points where the crest of the incident wave and the trough of the reflecting wave are farthest apart. So here's an antinode, and here's another antinode. That information takes us through the bulk of chapter 12. Our next chapter will take a look at sound.